What is up, everybody? Today's MCAT/DAT question of the day, because it's a chemistry question, so it applies to MCAT and DAT, is related to chemistry. And the thing I'm going to say is, this is from one of my professors at Berkeley, Professor Angelica Stacy. And I took an introductory chemistry class with her, and she's phenomenal. Really, really amazing professor. Really knows how to teach really great concepts. And that's what you're going to see in this question. It says a sample of CO2 is sealed in a metal container at 300 Kelvin. The pressure in the container at this point is 6 atmospheres. What is the estimate of the pressure inside the container if the gas is cooled to 100 Kelvin? The thing you should know is at 100 Kelvin, at this temperature of 100 Kelvin, CO2 is a solid. So, with that being said, let us now understand what the key concept is. So this concept is testing us about the ideal gas law because it seems to be about a normal derivation of the ideal gas law. And the ideal gas law, as we know, is equal to PV equals nRT, right? However, there will be a lot of ambiguities here. So let's go into those. The first ambiguity that we're going to talk about is just the derivation of the ideal gas law. Well, I mean, not the derivation specifically, but the derivation of the thing we want. Because right now we are dealing with this thing called PV equals nRT, right? In PV equals nRT, the only thing that has changed in this problem, if you look at this problem, the only things that actually change are pressure and temperature. The volume stays constant, the moles stay constant, and the ideal gas constant stays constant, right? That's the volume, that's the moles, and that's the ideal gas constant. And those are all constant. So if we do assume that the moles of the gas, and then we also assume that the volume of the container are constant, then notice that this whole thing, this PV equals nRT expression, we can change it into P over T is equal to nR over V, right? And remember, R is already a constant. And if we assume that N and V is a constant, then this whole right side becomes a constant. And so the corresponding formula at any point in time, assuming that the moles and the volume is constant, is that the P1 T1 has to equal P2 T2, right? And the reason for this is because this constant is never going to change. If anytime you have a pressure, if you put that over a temperature, it has to equal this constant. If you have another pressure and you put that over another temperature like P2, V2, then those two both also have to equal the same constant, and therefore they have to equal one another. But now let me bring up some subtleties that we have not talked about yet. This formula that we just derived, P1 over T1 equals P2 over T2, this is derived from the ideal gas law, right? We just took it from the ideal gas law. But remember, the ideal gas law, first of all, it only applies to gases, right? And more importantly, only applies to, usually ideal gases, which means very few intermolecular forces and negligible volume. But in our case, you might notice that we do have a difference here. It says at this temperature, CO2 is a solid. So we're not necessarily dealing with gases all the time. We're dealing with solid sometimes. So I want to make sure you understand that conceptually, but I also want to make sure you can visualize it, right? So in our case, we have two different samples. We have one sample at 300 Kelvin and another sample at 100 Kelvin. At 300 Kelvin, we have a gas, right? You notice how it's gas? And when we have gases, I drew this, this blue dot is a carbon, and then the green dots are oxygen. So you can see that this flask basically has a ton of gas molecules flying around, right? And in the gas law obviously applies to gases. So in this case, the gas law would apply because we are only dealing with gases in this case, right? Because there are gases that are floating around, and CO2 is relatively nonpolar, and therefore it's working out. Like the gases will be moving. But at 100 Kelvin, notice how we now have a solid. Solid means that all the molecules are scrunched up together in one place. When you're a gas, you have no definitive shape or volume, and you can expand. But as a solid, you have a definitive shape and volume, and therefore you're stuck in one place. And again, because there's not a gas here, the gas law does not apply. Okay? And if the gas law does not apply, I want you to think about that, right? I want you to think about that because this is the gas form at 300 K at this lower left corner. And remember, if you know what pressure is from physics, which you should because physics is a part of the MCAT, pressure is force per unit area. In other words, pressure is the amount of force that these molecules exert on the walls as they're moving around freely, right? Because they're going to be going crazy and they'll be hitting the walls all over the place. So there will be a pressure here because there will be a force that attacks the area of the entire container. On the other hand, when you have a solid, right, In the solid state, if you look at the top blank I'm filling in the solid state, molecules are not hitting the walls. They're stuck in one spot, right? And because they're stuck in one spot, the pressure is non-existent, right? You can think about this in the sense that, like, if you have a bunch of little kids in one room that are super hyper, they're going to be moving all over the place. But if you have one lazy adult in a room, he or she will be stuck at one place. It's tending to inactivity. And remember, pressure is force over area. And if molecules are not moving around and they're not hitting the walls with force, even if the area exists, the force is pretty much close to zero. And therefore, if there's no force, there has to be no pressure because all the molecules are stuck in one place. Okay? And I think you guys are starting to see what the answer is going to be in this case. Because in this case, the gas law applies and the gases are moving around really quickly. But the moment you convert that gas into a solid, the solid is going to be scrunched up into one place. The pressure will be about zero. Okay? Because there's no force. The force on the container walls is about zero. I mean, you might say that there's a little bit of force that the molecule exerts on these parts where it's sitting on the walls, and I would agree, but it's pretty much negligible compared to the force that is exerted by these molecules when they're going crazy in this container. And so if the pressure is about zero, the answer is the thing that we have to find that is the closest to zero. And in our case, believe it or not, that is answer choice A. And I really love this question because it really tests your ability to apply the ideal gas law. You don't want to memorize random formulas and just apply those formulas. You want to make sure you're conceptually understanding the point. You know that ideal gases only apply to ideal gas laws, and you can't do that if you have a solid. And then you have to think about, what does pressure actually mean? Pressure means force per unit area. And if you have a solid, the pressure on the walls is going to be much less significant than the pressure if you were in a gaseous form and the molecules were going crazy. With that, I hope you guys enjoyed the video. Please subscribe, comment, like, and I'll see you in the next one. Hey, thanks for watching the video. Really appreciate it. You want to check out any of my other videos, there's going to be one right here. Another link to one of my videos right here. And another video right here. Why not? I'll put one video right over here. And last but not least, if you want to subscribe to this channel, really appreciate it because I'm still an early YouTuber trying to get it down. But a subscription button should be right over here. So please subscribe. Cool. Thanks. See you guys in the next one. Hope you find these videos helpful.